Yes, I did.
Okay, great.
I got that on film, by the way.
I didn't fill the form either.
Oh, okay.
Give it a bullet.
There you go. Okay, so thank you all for coming to the seminar today. We have, our schedule is nearly out. If it's not out already, we have a few additions that we'll make, but we'll keep everybody posted on that. I'm thrilled to have Sandrine Matiasek here today as our first kickoff speaker. She's gonna set the bar high, and we appreciate it. So Sandrine did her undergraduate and master's degree in France at a university that I probably cannot pronounce, so we'll leave it at that. And she did more master's research at University of Belfast and her PhD at UC Davis on organic compounds in ag watersheds, ag-related watersheds. She's also done work on stream water quality after the campfire. And she's here to explain to us bioswales, so we'll get the caption for the figure that's on her door. What is a bioswale? And this is additional research that Sandrine's been working on. So thank you very much for being here.
Thank you, Rachel. Thanks, everyone. Happy to be here. And thanks, Rachel, for running seminar this semester. So I'm here to tell you about, kind of give you an overview and highlights. Let's start over. Sorry. I was hoping the computer would behave. Perfect timing. Okay. I just need to switch real quick to this. Okay. Can we back up and pretend this didn't happen?
This is why. Right.
Come on.
God, make it happen.
Pretentious of me to try to use my own laptop. But hey, that was quick, huh? All right, so I'm here to summarize, give you some highlights of my research, my main research focus at Chico State, which is on urban stormwater and how to deal with it. And we're going to focus mostly on one bioswale. And if you haven't learned what bioswale is yet, just hang on tight. Okay, so this work was initially funded by an EPA P3 grant, and it has involved over 24 students over the years at Chico. So you're seeing year 1 and 2 here, and then year 3 and 4 and 5. And the groups are growing, and I'm just very grateful for all the help of all these smart research collaborators I get to work with. All right, so we're going to talk about urban watersheds and what the problem is in terms of hydrology. And then we're going to talk about biofiltration as a potential solution, way to manage this urban runoff. Most of the talk is going to be focusing on the Butte College Bioswale and how it's performing. And then things we learned from monitoring the bioswale is that the nutrients can be problematic. And so we've been doing work in the greenhouse to try to improve that nutrient removal. And then we'll focus more on metals, where they're going in these systems. And then we'll see if these bioswales are they really all they're promising. All right, so in urban environments, we have an issue that is linked to impervious surfaces. These hard surfaces that don't let water in. So because of the increase of impervious surfaces in urban environments, we're seeing a decrease in infiltration from as low as 10%, decrease in infiltration and an increase in urban runoff. And runoff can increase from 10% in a natural environment with vegetated soils to more than half of the precipitation running off in a densely urbanized system. So that's problematic, and that's coined the urban stream syndrome. This syndrome comes with a set of symptoms. One of the main ones being flashier streams. So these urban streams are much flashier than a natural watershed system. with higher peak flows during storms and drier base flows between storms. In addition, these streams have a high erosive power, leading to more stream bank erosion. They have higher pollutant loads, and they have altered ecology, very different systems. So it doesn't have to be just like the LA River, which is what's pictured here, which is kind of the ultimate urban stream syndrome symbol. It doesn't have to be only in this problem isn't only occurring in large cities. It's also something we see in Chico, a smaller city. But you're familiar with this location? This roundabout is right down the street, right here. And on intense rainstorms, we're seeing flood problems. And we're seeing large pollutant loads, right? This is the corner of Celestino's, and it's always been the one with the highest spikes of everything. E. coli, you name it. You wonder why, right? I don't get to say that when I talk about this to other audiences, but you know this place, so lots of urban waste. All right, so we've been monitoring the composition of urban storm runoff in Chico over the last 4 years, and it takes a brave team of students ready to roll at some random times on a Sunday. I think this was the first storm on a Sunday. You know, we needed some extra help. So I'm grateful for this help. And what did we see? Well, in terms of metals, we're seeing high variability of metal concentrations, with zinc being the dominant metal, followed by copper, nickel, chromium, lead. And as you can see, there's lots of exceedances of these environmental screening levels, which are ideal guidelines for healthy aquatic environments, as high as 30% for lead and copper. So high variability and some problematic composition. In terms of nutrients, it was similar. We are seeing high variability. So this graph is kind of blank like this on purpose. It's to show you the extremes. So we have some kind of average low concentrations, but then some really high peaks of concentrations there. And carbon is the dominant. Organic carbon is one of the dominant nutrients, as well as followed by nitrate. So high variability. Another type of commonly found pollutant in these waters are petroleum hydrocarbons. And I don't have a whole beautiful detailed data set to show you. However, you should stay tuned, because one of our team members, Bryce, is working on setting up a method so that we can detect and quantify individual hydrocarbons in these waters. So we presented this research at AGU in December, and stay tuned for more this spring coming from him. All right, so, okay, we have this set of symptoms in urban streams. What could we do to manage this water? If only we had a way to let water back in the ground, right? Oh wait, that's what soil is for, right? And plants too, and microbes. So the stormwater biofiltration systems are systems, they're called green infrastructure, that are ways to manage stormwater in a way that mimics natural watershed processes. It's using plants, soils, and its microbial population to infiltrate the stormwater and retain its contaminants. So we actually have a lot of these systems around town. They're growing, and around town and its surroundings. So Butte College has this beautiful bioswale, and you're going to hear a lot about it in the coming slides. We also have a rain garden at Chico State near the Student Services Center. Maybe you've seen it. And as you can see, the terminology of these systems kind of varies. Rain garden technically has more of a creek bed, so it's got more rocks than a bioswale, which is more vegetated. And I call all of these systems biofilters, because they're meant to take in the water and treat this water. We've also been studying this municipal parking lot, which is the city lot 5 by the farmer's market, which has a set of porous pavers under cars here, and then it's also a mini bioswale system. So we've also gone a look at this one. So over the years, we've been monitoring the performance of these systems. They are growing in popularity, but they're not often evaluated for their performance, especially as far as pollutant removal comes. So we're focusing a lot on pollutant removal, but as you'll see, the hydrology is also very important. And then finding out about the limitations of these systems, we've been complementing with greenhouse experiments like this one, where we're looking at the role of certain amendments that we can make to these systems to improve nutrient removal. And then finally, we've been looking at the fate of metals in these systems. Where are the heavy metals going? If they're not in water, where are they? So that's what we're looking at. So we're very lucky to have a beautiful bioswale at Butte College. Anybody familiar with Butte College? Anybody transferred from Butte College? Yeah, so you know the parking lot, the student parking lot, and maybe you visited. There's this large 5-acre parking lot, which is the main student lot, which will have its runoff collected into 5 different inlets, which are those arrows, into a nice long bioswale, which is 900 feet long. So the first phase of the system was built in 2 phases. First phase was built in 2012, and that was phase 1 right here with these 3 inlets. And it kind of ponded around here, making a seasonal wetland. And then in 2017, there was this phase 2 that was built, and I'll show you some pictures. So this coincided with my grant coming in and having funding to do this research, and finding this ideal site was kind of a very fortunate circumstance, and also very fortunate to work with a great team at Butte College, led by no other than Dr. Mike Matiasek, who's my husband. And so we've had this fortunate collaboration with a great way to involve students at Butte College. And I'm not doing that really, that's his job. But Butte College students get to be involved in research, and some of them presented at the poster session, at the College of Natural Sciences poster session. And then some of them transferred to Chico and continue working on this project, like Gabby, who you will hear about soon. So it's been a fun project. And I'm very grateful for this system, for this collaboration. So this is a view of the bioswale in its entirety. It's kind of hard to see, but you see the parking lot over there with the solar panels. Phase 1 is the yellow vegetation that you see here, and then phase 2 continues. Here is the outlet. This was as it was recently built, and you'll see more pictures that have a lot more vegetation than this. And then this is a closer look at phase 1, and you can see how some of the you can see the inlets really well because they're sticking out with some plastic or cement structure. And these are inlets, some flow measuring devices that we managed to purchase and install thanks to a student learning fee with the College of Engineering. We have installed these flumes and weirs to measure flow. Inflows coming in and outflow coming out. And as you'll see, this has really expanded our abilities to understand how the system works, because it's not just about concentrations, it's also about load. So we'll learn about the difference in a second. All right, and this image is really cool to show you that water can be nasty, right? This runoff can be pretty nasty, but it can also be a beautiful day to come and download some data, like this day here in the spring. Okay, so I'm going to show you some highlights of last year's storm season, and it's pretty representative of what we've seen over the previous years as well, with some differences, which I'll highlight in a second. But this was the first big rain event of the last stormy season, which was November 2018. And as you all know, probably from being local, this was as the campfire was still burning, and we were sampling with masks. These are Butte College students, brave souls, who helped sample this November 1st sampling event. You barely see a vertical line here. That was the very first flow of water in the system. So these first flush events, the first rain of the season is typically the nastiest, and that's what I forgot to point out when we were looking at composition of stormwater. All the extremes on these previous graphs were these first flush events, right? The rain is finally rinsing out the landscape. So one big question we had at that time was, okay, is this water going to be worse than usual? And the short answer is no. Even though the fire was right at the border of the Butte College campus, and firefighters fought actively overnight to keep the campus safe, we didn't really see, in terms of concentrations, we didn't see higher concentrations of metals as far as metals go, for sure. Nutrients, yeah, I think nutrients were about the same too. So it wasn't the worst in terms of concentration, which was a bit surprising. But okay, so just to point out here, we have two sampling events. We have the rising limb here, the very first water flowing through the system, and then we came back towards the end of those storm days and sampled what we're going to call the falling limb, so towards the end of the storm. And what did we see? Well, we found that, again, lots of variability. So this is metal data. You're going to see a bunch of these graphs where I'm showing you for each element. So there's 5 different metals shown here. You're seeing the distribution of concentrations in the inlets, and then this little bar is the concentration at the outlet. Within each bar here, there is the median shown as a horizontal bar. So what you're seeing is that during the rising limb, the system really acted as a reservoir, a sink for metals. We are seeing lower metal concentrations at the outlet than the inlet. And that's a good thing, because these concentrations were pretty high. You know, lots of exceedances of environmental screening levels. And overall, the system was working well. It's interesting to point out, this is a bit of a detail, the copper wasn't cleaned up enough. So at the outlet, copper concentrations were still higher than recommended. Take come back a few days later, during the falling limb, we're seeing something very different. We're seeing that the concentrations overall are lower. Look at the axes, you're seeing orders of magnitude difference. But we're now seeing an increase between the inlets and the outlet overall. So now the system is acting as a source of metals. That's interesting. And that's something we've been noticing, not necessarily on a given storm or on a given date, but my current hypothesis is that this is very much driven by antecedent moisture conditions. So we've seen this also in the springtime, during spring storms, after quite a dry period of time. So if the previous storms is a few weeks or months ago, we've been seeing this kind of behavior for metals. Yes?
Good question. But on the second storm, the 23rd of November, it's true the outlet's higher, but you're dealing with 1 microgram per liter difference or several. So is that, I don't know about the metals, is that within, maybe not error of measuring, but maybe not so significant versus
Yes.
the comparison on the other side, you're almost an order of magnitude.
It's a great point, right? So this isn't as bad. I mean, the fact that the swale, the bioswale is acting as a source isn't as problematic as if it were during this storm, right? Because the inlet concentrations are relatively low, and nothing is exceeding those environmental screening levels. So yes, the swale acts as a source, but it's still within an acceptable range. Yeah. And we should keep that in mind. This all comes into play when we look at load, when we take into account volumes of water. Yeah.
So you have a lot of samples in the end to give you that range. Why? It only appears you have one sample for all the outs, or is you only just showing the
Yeah, so I'm showing one sampling time on each graph, and then the inlets, we have 5 inlets, but the outlet there's only one location. Yeah.
Okay.
So we have a range of concentrations because there are 5 different inlets,
Gotcha.
but not at the outlet.
Thank
Yeah.
you.
Great. All right, so now let's look at the same thing but for nutrients. For nutrients, I was a little surprised on this storm because the bioswale acted as a source in both cases. And we're seeing this, and there's a difference in concentrations between the first flush and the falling limb. So there's lower concentrations of carbon and nutrients during the falling limb. And generally speaking, the system isn't doing a great job at removing nutrients even at the beginning of the storm. And I was surprised by this because that's not always the case. Usually in the fall, we see during those first storms, we tend to see a removal of nutrients during the first ones. So that's interesting. But the general take-home message from this is that nutrients are not well retained by bioswales. The bioswale, and I'll show you further storms, later storms, where the bioswale acts as a source for nutrients very often. And this is not too surprising when you think about it. You have water flowing through vegetation and soils, and maybe some of that vegetation can be a source of nutrients. Maybe there's some leaking of nitrate going on. And this is not a fertilized environment, so there's no fertilizer directly involved. But there could be some nitrogen fixation and deposition and other processes. And this is a pretty well-known limitation of vegetated biofiltration systems, and that's what triggered our efforts in the greenhouse that I'll tell you today. Okay, so now we are switching to March. We went from November to March, and we're very excited because we have a weir system at the outlet. We finally have a way to measure outflows with this fancy weir setup. And now you're seeing, previously there was only a few inlets that we had flow for. Now you have all 5 inlets and the outlet, and you're seeing precipitation on top here. And so we're finally able to get a water budget for the system, and we're getting our final number. During this during this storm, which is in the shaded zone here, the bioswale was able to decrease storm runoff volumes by 78%. That's awesome. That's great. That compares to what we see in other systems in the literature. But some systems can perform like as low as 30%. So we're very pleased by these numbers. How did that compare to what was going on with the water composition? Well, so I'm showing you data from only the rising limb, that vertical gray bar here. This is where we got to come out and sample. And we're seeing something pretty nice here. We're seeing a decrease of metal and nutrient concentrations during the rising limb. So everything's lower. We had some exceedances for lead and zinc, and they got taken care of by the bioswale. Great. Okay. So this is not like every spring storm we've sampled. Sometimes in the spring we're seeing the system acting as a source of nutrients and even metals. So I think so there's still a mystery, there's still some mystery going on. And it might not be just hydrology. There also could be some seasonality to it. So there's still more to be done. So the wonderful thing about having good numbers for flows, being able to monitor inflows, inlet, incoming volumes over time, and outlet volumes over time, is that you can get the pollutant load, which is a mass of pollutant over a certain time frame. And maybe you remember from your chemistry courses, concentration is mass over volume, right? So mass over volume times volume over time for flow, that gives us a load, mass over time. So by taking these two pieces of information for each storm, we're getting a load reduction. We know the incoming load in the system, and we calculate the outflowing load for a pollutant. And so we got to do this for 5 storms in last rainy season. And overall, the system does take care of a lot of issues. So we on average, the Bioswale removed 79% of metal mass inputs and 42% of the nutrients. These red ones here is when the concentrations at the outlet are higher than the inlets, and that the flows don't work out. The bioswale is letting out, is not infiltrating a lot of volume, and it's still letting lots of water out, right? And so the lowest performance, the lowest values you're seeing for each element or contaminant was that falling limb in the November storm. So even though it wasn't too bad, the concentrations weren't that high, there was still enough water flowing out that the system as a whole was a source of nutrients. Okay, so this is where we're at with the Butte College Bioswale. It's been a fun ride, but we still have some mysteries, right? We still have some things to figure out. And so this took us to the lab. Oh, sorry, I forgot. I'm forever grateful for Eric Dearden, who graduated last semester and did his honors research, and he was the student behind setting up all these pressure transducers and measuring the flows. So he did a great job. Okay, so then we moved on, or in parallel, we went to the greenhouse and built these experiments in mini bioswales. We built biofilter columns, and I'll show you a picture in a second, out of PVC pipe, and we built them kind of similar to what biofilters are built with in general. So it's a mixture of soil and sand. The sand is here to help with infiltration rate. We have a little layer, an organic layer on top, and some sedges. Santa Barbara sedges are common wetland plants that are used in bioswales. We are conducting these experiments in triplicate, so 3 columns for each additive, for each parameter we're studying. And we're comparing different additives, which are those little blue diamonds in this case. We're testing some interesting materials. We're not just going to the store and buying the fanciest material that's been synthesized to try to remove nutrients. We're using waste products from other activities. And so we're looking at zerovalent iron, which is nothing else but iron filings, right? So if you're working for a metal shop and generating a lot of metal filings, you could have quite a lot of this iron dust. We're also looking at water treatment residuals. These are not often thought about, but anytime we're using surface water as a source of drinking water, this water has to be treated. And it's a little bit similar to wastewater treatment, except there is no human waste to remove. It's only natural organic matter compounds that are removed before the disinfection of water. And you're left with this solids. It's an alum sludge, and it's been known to be good at removing phosphate. So we're testing that in these filters. And the final type of material is biochar. We have 3 types of biochars. They kind of look like this, all of them. This is charred material, but it's not just like ash in a fire pit. It's material that's using waste materials from orchards, like walnut shells, or from rice fields, and logging residuals, meaning wood chips, and they're burnt in a low oxygen environment through pyrolysis to generate this highly porous char material. The best way to think about these is that they're similar to your Brita filter. If you have a Brita filter that's made of activated carbon, that's the type of char that's used to treat water. So we're testing all these to hopefully help remove more nutrients in bioswales. And the idea would be that when we're building a bioswale, maybe there's a way to sprinkle these in, or to add sponges made of these. All right, so we're in the greenhouse at the student farm. We have these nice columns built with these different amendments, and we're applying a synthetic runoff. So here we're not just applying rain, we're making it so that we know exactly what we're applying, and we're measuring what comes off, what comes through these filters. These are worst case scenario concentrations. The nitrate in particular is much higher than what would be in rain or in the storm runoff. And that's in part due to the fact that the water at the greenhouse is very high in nitrate because it's groundwater in a farm. All right, so what are we finding? I'm just gonna show you both graphs here. It's a bit much, but bear with me. So you're seeing different applications. There is 4 different applications shown here. So these are different time frames, and each treatment is shown on the horizontal axis, along with a control, which is a set of 3 columns that have no additives. And generally, we're seeing a really high variability in nitrate removal. What I'm showing you here is percent removal. So these are percentages. So 100% means we've removed all of the nitrate, right? So focusing on the nitrate first, we're seeing really high variability between applications. Something else is going on. Even the controls, they're all kind of either working pretty well or working pretty bad, pretty poorly. But overall, if you compare the treatments to the controls, we can see that there's a general improvement thanks to the amendments, the additives, compared to controls. What's interesting is on the phosphate side of things, phosphate, if you look at the y-axis, we have some very large range of percent removal. And what would a negative percent removal mean? That means we have additional phosphate being leached and released in the water, right? That is not what we're looking for. And that's something we've been observing for biochars a lot, but also the controls. You're seeing how controls were releasing more phosphate than we were applying. So for the first year of this experiment, really, we've seen a pretty consistent release of phosphate from these columns. But we're seeing that the columns that are amended with iron and the water treatment residuals are actually working really well, with as high as 93% removal for iron and 82% on average for the water treatment residuals. So that's good news. And
Quick question on this slide.
Yes.
For you, the February 22nd, when the nitrate removal seems to screw up your trends on all of them.
yes,
What happened?
no idea. So there is the finer details is that the first 3 editions, October, December, February, were all done the same, which means we were hand watering these and keeping the plants. So between applications, we were going to the greenhouse to keep the plants alive and just watering with water. But that watering was not very regular, and so there could be something that I think it's a change in soil moisture. Something was going on. I still think that this variability is really due to soil moisture conditions. I can't really show this here because we didn't measure soil moisture every time we applied. The bigger change is that October 2019 application was after a summer where we switched to irrigating. So we have little irrigation tubing for each column so that we kept our plants alive over summer. And I think that's that's helping remove nitrate. That's why we have the latest application with really high % removal, because generally weather conditions, I think, help with nitrate removal, with denitrification in particular. And it's interesting because it seems to also affect phosphate removal. So I think that's why the control switched to a positive removal, and some of the biochar also.
What did the control column look like?
The control columns are the same as, they look like this, they just have no amendment. So they still have the soil and the
Sand and mix.
sand, everything else. Yeah, they're just not sprinkled with those other materials.
So
Yeah, so to be continued.
Before you measure this, were the columns dry? Mostly, or were there?
No, they're usually they were watered a week before the application.
Okay.
They were watered the day before.
Okay.
Yeah, but they're moist, but they're not terribly moist either.
Okay.
Yeah. But this is something. This is the inspiration for more research. We're gonna start tightening up as far as moisture content is concerned. All right, and this hard work is mostly carried out by Nora Pizzilla, one of our environmental science seniors who's finishing up this year, and she's hiding from my camera most of the time, so that's the best picture I had. All right, so in our last 10 minutes or 5, we're going to finish with talking about metals. And this was, this is a 2-part story. We started thinking, okay, the metals are generally well retained by bioswales. They are removed from water, but where do they go in these systems? Well, we started by doing another greenhouse experiment where we looked at the role of 5 native plants. All of these are here, commonly used in bioswales, and we built biofilters in very similar fashion as what you saw for nutrients. This was the work mainly driven, Bryn Copson, our environmental science major from 2 years ago, mostly led this charge with help from Eric. And we were applying synthetic runoff again with known concentrations of metals and some nutrients for good measure. But we focused on the metals here. And the results of this effort, so this was 6 applications over the course of 5 months between 2017 and 2018. As far as the water was concerned, it was really good. We had 99% of the metals that were applied that did not come out of the filters. So the metals were staying in those biofilters. They were removed from water. Great, but where are they going? So first we looked at the soil. And so this graph takes a little time to wrap your head around. We have the green horizontal dashes here are the initial contents of metals in the columns, in the soil that was used, in the media that was used to build the columns. So that's our starting point. And then at the end of these 5 months, we had concentrations of metals. These top blue dots are in the top soil at the surface of the filter, the biofilter, and then the red dots are the ones that were at the bottom of the columns. So we destroyed these columns, collected the soil on top and at the bottom, and we're seeing an accumulation of metals at the top of the columns, which makes sense because that's where the water was applied. But we're documenting an accumulation of metals in the soil phase, right? And then we also looked at plants and whether the plants were picking up, were uptaking metals in these greenhouse experiments. And we also saw an accumulation of metals in the plants, specifically in roots. So here you're seeing 4 types of symbols. You're seeing roots and shoot concentrations for each metal. And the blue letters are the initial contents, and the red letters are the final contents after those 6 applications. And generally, we saw an increase of root concentrations for all of metals, except for zinc. Zinc was kind of all over the place, no real difference, and not real accumulation of zinc based on these tests. So that was interesting. However, these were greenhouse tests. So when Gabby came in and told me, I want to do metal fate in the bioswale itself, because I know Butte College, I know this bioswale, we went for it. And so we moved this test, this experiment to the field, and now we're studying the metal accumulation in plants that are live in the bioswale. So thanks to the Butte College team, there's some beautiful deer grasses and other plants that are thriving in the system. And Gabby periodically goes in and snips a little bit and gives them a hard time. But we're studying the sedge, some deer grass, spreading rush, and all of these are spread out across the bioswale. So we're looking at them throughout the system, not just one location. And we have 6 specimens of each plant. All right, so through careful sampling and rinsing and grinding and digestion, Gabby then sends those samples to UC Davis for ICP-MS analysis, which she won't need to do anymore since now we have one of those, and we've been learning to use the instrument, thanks to Johan. So there's Gabby in action. Thank you, Gabby. And here is her data, some of her results. So we are seeing a seasonal accumulation of metals, mostly in roots. So the root part comes next. But for now, you can see how the darker purple bars are the October concentrations in those plants. And then the red bars are the contents of metals after a full season, a full storm season. So we're seeing an increase of metal content in the plant. And then zooming in a little bit, distinguishing between roots and shoots, we are seeing a general accumulation in roots. Those are the cream or orange bars here, as opposed to the green bars. And this is generally, zinc is definitely still the exception. We're seeing similar patterns as to what we're seeing in the greenhouse. So that's interesting. And it could be something that makes sense based on the fact that zinc is an important element for plant metabolism, so probably more mobile than other metals. We can't really call this phytoaccumulation just yet. Phytoaccumulation is a term that relies on a certain ratio of concentrations in the shoots above ground to the roots, and so far we're mostly seeing an accumulation in roots, not in the above ground vegetation. So not just yet. So in conclusion, what have we learned? Well, the Butte College Bioswale is a really great environment to monitor how a bioswale works. It was built for education, and it's been working out great that way. It's also doing its job. It's reducing flood risk. It's decreasing storm flow volumes by as high as 78%. Overall, it decreases metal and nutrient inputs, but we are still trying to learn how that happens and when, and whether the antecedent soil moisture conditions are an important driver. In terms of nutrient removal, we are seeing some help from different additives, especially zerovalent iron and the water treatment residuals. This is interesting in terms of sustainability, because this would be a way to repurpose a waste material or several waste materials from other activities. And finally, as far as metal goes, the metals are going in the soil and in the plant roots, as far as we can tell so far. All right, so the promise, the future is swell for runoff, right? So just to highlight once more, I'm very grateful for all the students involved. Also grateful for our wonderful GEOS staff that make all this possible, right, Bill? And we've gotten a lot of support from the Center for Water and the Environment. That's where our greenhouse experiment started. Initially, we were not in a greenhouse, we were in an office, right, in Holt. We've gotten a lot of support from various funds from the university, as well as the Water Resources and Policy Initiatives. And yes, that's it. Do you have questions? Thank you. Yes.
So you did the calculations on the amount of water, or I'm sorry, the amounts of metals that were being introduced, using the weirs and the concentrations through the inlets. And you showed that obviously metals are being uptaken by the plants. Have you done any estimation on the mass of plant material so you can get an estimate on the amount of metal that's being uptaken now?
Yeah, so that's the long-term plan, right? So looking at total bioswale domination or understanding would be to have a full budget for water, which we are getting close to, we're getting there, but also pollutant budgets. So for metals, but also for nutrients, how much is exported through water, how much is infiltrated and going to the groundwater. And this is one aspect that I haven't described in this talk, but we have one of our master students who's looking at the composition of the pore water, soil water. But then what about soils? How much of these contaminants, for each contaminant, how much will stick to the soil? And then plants, what kind of budget? So there's a budgeting aspect that we'll get to, or an upscaling exercise that we're getting to, but first we need to continue collecting a little bit more data. That's a great question.
Continuing on that question, in Bryn's work, it seems like you'd be able to do a mass balance of where are the metals? Are they 50% in the soil and 50% in the roots? Or
Yeah.
were you able to do that?
Except that there was a miscommunication on this, and the biomass was not measured. So I don't have the biomass of the plants that were, and I don't have the mass of soil. I know what we put in. So for soil, for the physical media, we could do a rough estimate, but we didn't get the plant biomass.
On the roots and shoots uptake, it looks like you guys measured for what would be like the equivalent of a rainy season or something.
Mm-hmm.
Is there a max that deer grass can uptake in its lifespan?
That's
over
definitely
years?
a question that we want to get to. And so far, we haven't seen that maximum amount, or we haven't studied this for long enough. Yeah, but it's definitely that's one of the driving questions is, when do plants stop taking up metals?
Or die?
Yes, yes.
So, because phase 1 and phase 2 were built at 2 different times, the plants are younger in phase 2, but we're seeing comparable amounts and comparable increases in phase 1 and in phase 2. So, even though the phase 1 plants are a lot older, we're still seeing that uptick in the spring. So.
Perfect, thank you for that. Yeah.
State change in pH is the beginning of the storm event, the end of the storm event, which leads to the removal of nutrients, or suddenly the source of nutrients again.
It's a great point. I didn't show pH data. It doesn't change dramatically, but we all know that a small change of pH is actually larger than it seems, because it's a log scale. And that's something I should look into more. Yeah, there could be enough of a pH change to, yeah.
All right, well, thank you so much, Sandrine.
Thanks, everyone.